Hello and welcome to another Algebra 2 video by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 1 on shifting functions. Unit 8 is all about the transformation of functions. And you've dealt with this before in Algebra 1, so let's get right into it and start discussing it with the simplest of all transformations, which is simply moving a function around vertically and horizontally. Here we go. Translating or shifting functions. The basic transformations of translating, otherwise known as shifting, reflecting, rotating, and dilating can all be done to the graphs of functions by algebraically manipulating them. Rotating functions is out of the scope of our work in this course, but we will investigate all the others, all of which you originally saw in Algebra 1. In this lesson, we will concentrate on shifting functions. So let's take a look at exercise number 1. Consider the functions f of x equals the absolute value of x, g of x equals the absolute value of the expression x minus 3 plus 2, and h of x equals the absolute value of the expression x plus 1, then minus 6. Letter A. Without using your calculator, graph f of x equals the absolute value of x on the grid provided. All right, great. Now, my claim is with a very simple functions like f of x equals the absolute value of x, you should be able to graph those without a calculator. Now, that doesn't mean you should graph them without a table of values. Feel free, right, in this kind of problem to do something like this. You know, I've got a little x, a little y, maybe I've got x equals negative 5, which the absolute value then would be 5, x equals negative 4, the absolute value would be 4, etc. All right. And then plot those points. Pause the video now and plot the classic absolute value graph. Okay, well, let me just move this for a second, right? And again, you could kind of flesh out a table, right? Gets very boring once we get into the positive values of x. And at the end of the day, right, we get a graph that looks like that. A very classic looking V shape. And what we really have is y equals x in this direction and y equals negative x in that direction. We're not going to worry about that too much right now. Now let's take a look at letter B. Using your calculator to produce tables of values, graph the other two absolute value graphs on the grid. Label each. All right, so here's what I'd like you to do. We're not going to go through bringing up the TI Inspire and creating the calculator graph and all of that and showing you how to lay out a table. We've done that lots of times in this course. What I want you to do is take your graphing calculator out. I would suggest putting actually all three of them in for comparison purposes, and then take a look at tables of values for both g of x and h of x and produce those on the graph as well. All right. Now you'll see a graph of g of x and f of x in your grid, and especially if you set your grid settings to be the same as what's on this graph paper, it'll be very helpful. Pause the video now and take a few minutes to do that. It's going to take some time to generate those tables. Awesome. Anyway, easy enough to come up with some tables. Now again, you know, we could have huge tables of values here, but those things are going to kind of be enough. And once I graph them on our graph grid, we get something that looks like this. Now notice for a second, g of x, which is the absolute value of x minus 3 plus 2, is this graph here that I have in red. And it's pretty clear that what's happened to f of x is that we've shifted it 3 units to the right and 2 units up to produce g. We've shifted it 3 units to the right and 2 units up to get the graph of g. Likewise, taking a look at the graph of h, it's very obvious that we've shifted that 1 unit to the left and 6 units down to get the graph of h. 1 unit to the left and 6 units down. Hopefully this is kind of like recalling some shifting patterns that you saw in Algebra 1 and that we saw a little bit earlier in this course when we looked at the graphs of logarithms that had been shifted horizontally. Anyhow, letter C, describe how the graph of y equals the absolute value of x would need to be shifted to produce the graph of y equals the absolute value of the expression x minus 6, then minus 8. Pause the video now, and based on what we saw in letter B, why don't you describe how the graph of this thing would be shifted to produce the graph of that. Well, again, notice that in G, when we subtracted 3 directly from the x, we shifted the graph to the right 3 units, and then when we added 2 to the overall absolute value expression, we then shifted the graph up 2 units. All right, likewise in H, when we added 1 directly to x, we shifted to the left 1 and then subtracted 6 overall, and we shifted down 6 units. So we can extend that pattern to speculate that we would need to shift 6 units right and 8 units down. And I just it's just driving me nuts. Oh, it stayed blue this time. Now, we oftentimes talk about what are known as parent functions when we are kind of referencing shifting or transformations in general. Y equals the absolute value of x is a parent function. It's the simplest of its variety, right? We want to know that graph so that when we then look at something like this, we can easily produce its graph by thinking about this one and then just employing the shifts that are evident in the equation. Let's keep working with shifting. All right, shifting patterns. Although we only use the absolute value function, the previous exercise illustrates the fundamental manner in which all vertical and horizontal shifts occur in functions. Let's take a look at those. Shifting graphs of functions. First off, vertical shifting. The function f of x plus k shifts the function up by the absolute value of k units for k greater than 0 and down by the absolute value of k units for k less than 0. All right, now before we go into the horizontal, let's just discuss the vertical really quickly. F of x, right, is just another name, this thing is just another name for y, okay? So the idea with vertical shifting is very, very simple, all right? If I take a function and I add a positive constant to it, I'm adding that positive constant to all the y values, so I'm just moving them up by that amount. On the other hand, right, if I subtract a positive number from f of x, then I'm subtracting that value from all the y values, and I'm shifting the function down. We're kind of like calling it f of x plus k, and then we're basically saying, look, as long as k is positive, it goes up, and if k is negative, it goes down. Now let's take a look at the horizontal shifting. The function f of x plus k shifts the function left by the absolute value of k units for k greater than 0, and right by the absolute value of k units for k less than 0. And again, the way that you really want to kind of think about this is, when we add a positive number directly to the x variable, before anything else is done, we shift the graph to the left by that many units. When we subtract a positive number from the x variable directly, then we shift to the right by that many units. And that's a little counterintuitive, right? The vertical shifting works exactly the way you want. Add to the function, go up. Subtract from the function, go down. On the other hand, the horizontal shifting, if we subtract from the x variable, we shift to the right, and if we add to the x variable, we shift to the left. All right, let's take a look at exercise number 2. The function f of x is shown on the grid below. A second function g is defined by g of x equals f of x minus 3 plus 1. Letter A. What is the value of g of 0? Show how you arrived at your answer. All right, well look, if they ever ask you what the value of a particular function is, and they've given you a formula for that function, what I want you to always do is use the formula. So try to do that, try to evaluate what g of 0 is by using the formula and the graph of g of x, which is sitting right there. Pause the video and give that a shot. All right, well let's take a look. We know that g of x is equal to f of x minus 3 plus 1. So g of 0 will be f of 0 minus 3 plus 1. That means g of 0 will be f of negative 3 plus 1. Now we have to use the graph of f of x to decide what f of negative 3 is. Well, f of negative 3, right, is going to be gotten from this point. We know that we have negative 3 comma 1. So that means f of negative 3 is equal to 1. And that means that g of 0 is equal to 2. Now, of course, what that tells me is that the point 0 comma 2 will lie on the graph of g of x. And really what it's doing, right, is it's taking this point that is at what, negative 3 comma 1, and it's shifting it 3 units to the right and up 1, right? That's what it's doing. So let's now take a look at letter B. Identify how the graph of f has been transformed to produce the graph of g and sketch it on the grid. Okay, so what we want you to be able to do is look at this particular definition and go, well, I subtracted 3 from x directly, and that does something. And then I added 1 to the overall function, and that does something. Pause the video now, identify what the transformations have been, what the shifting has been, and then use that to try to graph g of x. All right, well, the subtraction by 3 means that we're going to go right 3 units, and then the fact that we've added 1 overall means that we're going to go up 1 unit. What's kind of cool about that then is that you can take just enough points, right? Maybe this one, this one, this one, and this one, and you can move them over 3 and up 1, over 3 and up 1, over 3 and up 1, etc., and you will produce that graph. Right? It's simple. Once we know, right, what the transformation is, how the shifting has gone, it's easy then to take just enough points and shift them in the way that the formula indicates to produce our new graph. All right, let's keep going. Shifting patterns always hold. We can use these shifting patterns in a variety of ways because they apply to all types of functions. All types. There's not a type out there where I'm going to be like, actually, now the shifting patterns work in a totally different way. Every function that's out there, we can use these patterns on. So let's take a look at number 3. A function f of x has a domain of negative 3 less than or equal to x less than or equal to 10, and a range of y is less than or equal to 22. What are the domain and range of the function f of x plus 7 plus 10? Explain how you arrived at your answers. All right, well, what I'd like you to do is pause the video right now and see if you can figure out what the domain of this new function is. The domain, and the range. All right, well, let's talk about it. First things first, we want to kind of like look at this and say, okay, this is a shift of f of x by 7 units left and 10 units up. Now, I always want you to kind of think about the domain and range as being sort of a box within which the function lives. So the original function, right, lives within this box that kind of goes from negative 3 to 10 along the x-axis, all right, and it goes from 22 on down, right, if you will, on the y-axis. So it lives within that box. Now, when we shift the graph of the function, we shift the box within which it lives. So we're going to take all of these things and we're going to shift them 7 units to the left, right? 7 units left. And then we're going to take this thing and we're going to shift it 10 units up, right? So the new domain will literally be negative 3 minus 7 is less than or equal to x is less than or equal to 10 minus 7. So that is going to be x is greater than or equal to -10, less than or equal to 3. That's our new domain. And our new range is going to be y less than or equal to 22 plus 10, or y is less than or equal to 32. The box within which the function lives just gets shifted the way that the function does as well. Makes sense, right? All right, let's keep working on it. Exercise number 4. Given the quadratic function f of x equals x minus 4 quantity squared minus 5, answer the following questions. Letter A. How has the simple quadratic y equals x squared been shifted to produce the graph of f of x? All right, well, why don't you go ahead and see if you can answer that question. All right, well, since we've subtracted 4 from x before even squaring it, that means we've shifted 4 units to the right. And then we subtract 5 from the overall function, and that means we've shifted 5 units down. So we're going to say 4 units to the right and 5 units down. All right, letter B. Given y equals x squared has a turning point at the origin, 0, 0, where must the turning point of f of x lie? All right, so yet again, y equals x squared is a parent function. It's a very simple function, right? Opens upward, has a turning point right at 0, 0. Now, where will our new function have a turning point? Pause the video now and try to figure that out. Well, given that our new function is simply a shift of our old function by 4 units to the right and 5 units down, that turning point, which used to be at 0, 0, will now go to 0 plus 4, comma 0 minus 5, and therefore our new turning point will be at 4, comma negative 5. Okay, great. Letter C. Sketch f of x below and give the domain interval over which f of x is increasing. Great. Well, why don't you go ahead and give this a shot? All right, well, we know what y equals x squared looks like, or at least we should. So this thing now has a turning point at 1, 2, 3, 4, 1, 2, 3, 4, 5. And it has to look something like that. We don't need to have it look perfect. Maybe look a little bit better than that. I think I'm going to label the turning point. Great. And over what interval is it increasing? Well, it begins to increase from here on out. And we can really say that the interval is increasing in one of 2 ways. Now, I'm going to get jumped on by certain math teachers from this. We can either say, it increases x greater than 4, or x greater than or equal to 4. And again, I know that there's some math teachers out there that are very adamant one way or another. You know, some believe that you absolutely cannot include the 4. Some believe that you absolutely must include the 4. All right. Either way is pretty much acceptable. All right. I think most people sort of lean towards the don't include the 4 because at that point the parabola is level, right? So it's sort of like everywhere after 4 it's going up. But I claim if I'm going to walk up this hill, I'm probably going to start at x equals 4 and then start climbing. Anyway, whatever. Let's take a look at letter D. Which has a lower minimum value? The function f of x or the function g of x equals the absolute value of x minus 6 minus 10. Explain your choice. All right, well, pause the video now, and really without using your calculator at all, you should be able to tell me whether or not this function or this function has a lower minimum value. Okay, well, keep in mind, right, that g of x is a shift of y equals absolute value of x. Y equals absolute value of x, just like y equals x squared, has a turning point at 0, 0. So g of x has a turning point at 6 comma negative 10, f of x has a turning point at 4 comma negative 5. So g of x has the lower minimum because, if you will, negative 10 is less than negative 5. It's that simple, right? And the beautiful thing is, as long as we understand what the parent functions look like, as long as we know what y equals x squared looks like and what y equals absolute value of x looks like, we don't need to graph this one, right? We know, oh, that thing is absolute value of x that's been shifted to the right 6 units and down 10 units. So we know its minimum value must be negative 10. All right, let's keep going. One more problem here. Exercise number 5. The function f of x equals log base b of x is shown graphed below for some value of b. The function g of x is defined by g of x equals log base b of x plus 2. Letter A, what is the value of b? Justify how you found your answer. Uh-oh. So we're back to logarithms. I know it's been a little bit since we've seen them, like one whole unit kind of skipped, or maybe a couple units skipped over since we've seen logs. See if you can remember. Remember what a logarithm is, right? A logarithm is, gives you the number you would have to raise the base to in order to get the input. So what's a good idea here is to look at various nice points on this graph to try to think about the value of b. Pause the video now and see if you can figure it out. All right, well note, there are some nice points on here. That one's nice, 1 comma 0. This one's very nice, 3 comma 1. This one's kind of nice, 9 comma 2. And 1 comma 0, but that one doesn't really help us very much. The one that really helps a lot is 3 comma 1, all right? Because that really tells us that b is equal to 3. And it's equal to 3 again, because think about this for a second. If I have log base 3 of x, then, well, what power do I have to raise 3 to in order to get an input of 3? Well, I'd have to raise it to the first power. Likewise, if I put 9 in as an input, what power do I have to raise 3 to in order to get 9? Well, that would be equal to 2. So our base here is equal to 3. And that doesn't have anything to do with shifting or transformations. That's simply a little review of what a logarithm is. Letter B. How does the graph of g of x compare to that of f of x? Well, this does have to do with shifting, so pause the video now and go ahead and figure that out. All right, well, it's shifted 2 units to the left. Simple. No vertical shift, but shifted 2 units to the left. Awesome. Finally, letter C. Sketch the graph of g of x and its vertical asymptote. All right. Well, what's kind of cool is we've already laid out these 3 points that are rather nice. All we really have to do is kind of take those points and shift them all 2 units to the left. But the other piece that's rather helpful here is this idea of a vertical asymptote. Recall that when we have an unshifted logarithm, like f of x, it's always got a vertical asymptote of the y-axis, right? This graph is getting closer and closer to the y-axis and bending downwards towards negative infinity as it approaches the y-axis. That means if we shift the graph 2 units to the left, we're now going to have a vertical asymptote along the vertical line x equals negative 2. That's actually, in my mind, very helpful to throw in before we do anything else, right? We just put in that vertical asymptote at x equals negative 2, right? Now I can take each one of these marked points and I can just shift them 2 units to the left. So I could put this one here, and this one here. And then I can just do my best to make the graph actually go through them all and I can then get g of x. There it is. Not the prettiest one right here, but I almost made it through the point. Almost. All right, let's summarize. Now, you saw shifting patterns back in Algebra 1, and we even reviewed a little bit of them in this course already, ironically a little bit when we were looking at logarithms, and a little bit even when we were looking at exponentials, and we shifted them vertically in order to shift their horizontal asymptotes. So we've kind of already seen these patterns, and they work exactly the way that you want them to in the vertical shifting, right? If I add or subtract a positive number from the overall function, it moves it up or down the way you want it to. The horizontal shifting, as we'll see also with horizontal compressions and stretches, works almost the opposite of what you'd expect. When you add a positive number to x directly, it shifts it to the left, and when you subtract a positive number from x directly before anything else, it shifts it to the right. And that can be a little tricky, but it really gets into the difference between the input and the output role in a function, right? And the input role is very, very different, especially like, hey, I subtract 2 from the input before I even allow the function to tackle it. Well, that means I've got to now be 2 units larger on every one of my x values to get the same y value back out. And likewise, if I added 2 to x before I did anything with the function, then that would allow me to sort of start 2 units earlier to get the same y value. All right, well, we're obviously going to work a lot more with the shifting throughout this unit as we fold all of these transformations together as we work through the unit. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.